Welcome to today's webinar. The topic of this webinar is Advanced Multi-Emitter Radar Simulation with Off-the-Shelf T&M Equipment. My name is Rainer Lenz. I'm a product manager at the T&M division. Later on with the examples, Thomas Röder will help me. He's application engineer also in the T&M division. First of all, let's have a look at the table of contents, what you will see in this webinar. First of all, we will look at some application examples. Then I will present to you the graphical user interface of the Pulse sequencer software. In addition, we discuss contributions to real-world scenarios, and then we will have a look at some examples, pulses and sequences, emitters and localized emitters. We will see a direction finding example and how to configure multi-emitter environments. Let's start with some examples first. Let's look at the interference scenario at airports. There you have coexistence of primary airport radar, LTE base stations and weather radar stations maybe. In this image, you see how this environment looks like. The rotating antenna is transmitting pulses to the aircraft, and the reflections are also received by this radar antenna. But in addition, it is interfered by LTE base stations, for example, or weather radar stations. So this is a test case where you need to account not only for the radar pulses, but also for the signals coming from the base station, for example. In order to test this, you must generate this environment. You can generate the radar signals and the interference signals together and perform a conducted test. So you can include real-world effects like antenna patterns, antenna turns, noise. Once the signal is created, you can inject it into your radar receiver hardware directly and test if it can still detect the radar returns from the aircraft. Another example can be seen here. On this example, electronic receivers for electronic support measures shall be tested. Normally, if you have, for example, this Coast Guard vessel somewhere in service, you are receiving electromagnetic signals from various sources and directions. The processing unit at the Coast Guard vessel needs to identify the signals and classify them. So in order to test these electronic support measures on board, it's a pretty complex task. You can create all these signals by really generating them, or you can simplify your test case. In order to simplify the test setup, you can create the signals in a signal generator and directly transmit those signals to the ship in order to test the systems on board, to stress them and to detect if they're really working correctly. In addition, you can also directly inject these signals into a radar receiver and check if it can detect the signals and identify them correctly. Up to now, we only have seen one contributor. In this scenario, you see several contributors like ships, aircrafts, and also some ground-based stations. The aircraft, for example, is communicating with the ship. The ship is also transmitting signals somewhere. The other ship is also doing communication somewhere. In addition, on land, you might see a radar station which is also transmitting. Normally, you want to know what kind of signals are in the air. So people are using monitoring station in order to identify the signal origin and where the signals are coming from. So again, this is a pretty complex test case. So you need to test receivers with multiple signals. You need to test receivers with multiple antennas. And if you want to do direction finding, you also need to test the direction finding system. So therefore, you need phase coherent signals in order to do so. For this, there are solutions. For example, if you're testing signals up to 6 GHz, you can use various SGT-100A, which can be operated in a phase coherent mode, which produce up to 8 phase coherent signals, which can then be injected into a 8-channel receiver. If you are testing signals up to 20 GHz, you can do the same setup by using SMW200A equipped with SGS-SGU extension boxes in order to create up to 8 phase coherent signals up to 20 GHz and also to test your 8-channel receiver with those signals. So bringing everything together, what you have to do is you have to test your support measures, you have to test your receivers, you have to test your equipment in pretty complex signal environments. So what you need to do is you need to bring the field test to lab before. There are traditional approaches which are using big test systems. We are following a different approach. We follow the approach of using software-defined off-the-shelf T&M equipment. This helps you to reduce total cost of ownership as you do not use special systems. Turnaround time for service is lower and also maintenance cost is lower. Using off-the-shelf T&M equipment helps you to bring up availability of your equipment. In addition, you have synergy across projects by reuse of standard T&M equipment in various projects. So now let's have a look at the R&S pulse sequencer software, which basically allows you to create all these signals which we have seen in the examples before. First, let's have a look at the graphical user interface of the Rohde & Schwarz pulse sequencer software. This software has a toolbar which allows you to do all the standard operation like saving your data. It also has a wizard which guides you through the software the first time very quickly and allows you to create your signals very quickly. In addition, it has a project database where you have all your items which you're using in your simulation. For example, your configured pulses, your defined sequences, your antenna diagrams, and your emitters and scenarios. The software allows you to choose the simulation type which you're using. If you only want to use simple pulses, pulse trains, emitters, or localized emitters. In addition, you have the workspace where you see finally your scenario configuration, you have access to the waveform generation dialog, you assign your instruments, and finally you have also your simulation display. So now let's look what is contributing to real-world scenarios. First, of course, the signal waveform. This can be pulses alone, this can be sequences of pulses, bursts. In addition, you have modulation on the pulse. The emitters normally carry antennas. They have patterns like pencil beams, cosecant beams, or phased arrays. Also, the receiver can carry an antenna diagram. The antennas are having certain scan types like spiral scan, helical scan, or conical scans. As we've seen before, if you have various players somewhere, they have a location somewhere on a real-world environment. In addition, they're having a certain attitude information, and the antennas have pointing directions. If you are in a real-world simulation environment, you also have to account for the free space loss between the transmitter and the receiver. So let's look at the pulses and the modulation on pulse and some sequencing examples. This slide shows you how to define a basic pulse. The basic pulse normally consists of several items. In the software you have access to a timing tab which allows you to define rising edge, falling edge, and the width of a pulse. Then you have access to a level tab which allows you to account for overshoots or droops, for example. If you want to choose a certain modulation on pulse, you have access to a modulation on pulse tab, which nicely represents what kind of modulation has been chosen. In this example, you see a chirp signal, you see the IQ data at the top, and you see the spectrum at the bottom. So up to now, we have only looked at pulses. But real-world environments also can consist of different waveforms, like for example waveforms coming from GSM base stations. There could be waveforms coming from wireless LAN stations, there can be LTE base stations, and there can also be CW interferers. So also these signals can be accounted for. The Rohde & Schwarz pulse sequencer software allows you to import these signals into the software and reuse these signals together with the defined pulses. So now let's look at some typical modulations which can be used. We have all the standard modulations on board like AM, FM, and also ASK or FSK. For radar signals, chirp modulations are very important, so we have them on board. If you want to define your own modulation, you can use our equation dialog, which allows you to define your modulation by yourself. We also have BPSK or Barker codes on board or polyphase codes. UPSK is also available. If you want to add noise, you can do so. If there is still some modulation missing, we have defined an interface where you can plug in your own code in order to use this code then together with our software. After having defined the pulse and the modulation on pulse, you have access to a powerful sequencing tool. This sequencing tool allows you just to repeat a single pulse, or to repeat it multiple times, or to cascade several pulses. It also allows you to apply interpulse modulation on the defined pulses. You have access to some structures like loops or nested loops. They give you access to very long play times by just looping a pulse several times. If you want to have a loop in a loop, you can also do so. This is what we call nested loop. If you want to play two signals in parallel, we have access to a structure which we call overlay. This is extremely important, for example, if you want to use FMCW signals and pulse signals in parallel. So you can define this, and the signal generator will automatically play the combined signal. As we have seen before, the emitters and the receivers are carrying antennas. So also the software allows to define these antenna diagrams. Here are just 3 typical examples. At the top we have a cosecant antenna pattern, or in the middle we have a Gaussian pattern, and at the bottom we have a dipole pattern. You also have access to 2D cuts in order to verify if everything has been defined correctly. In addition, you have access to antenna scan types. So there's, for example, helical scans, raster scans, or circular scans. The Rohde & Schwarz pulse sequence software allows you to use these defined antenna diagrams together with the defined pulses and sequences before. Now, after having defined the antenna diagrams, the antenna scan type, the waveform, so to say the pulses, you can combine all those together to a so-called emitter mode with a beam. In the software, you would select your defined antenna pattern, you select the antenna scan type. Then you select your defined waveform. And in total, all this information is compiled into one emitter mode. You cannot use only one emitter mode. You can also have several modes on one of your multifunction radars, for example. So you have access to several modes. You can just extend the modes by adding another one. You can also have several beams, which can carry different waveforms. Each beam can have different offsets in carrier frequency, in elevation and azimuth for simulation later on. In addition, you can also define a receiver. This receiver can also carry an antenna beam, it can carry an antenna scan, and it also has, of course, a certain gain associated with the antenna. Also, the pointing direction of the receiver can be defined, as for the emitters. So now let's look at a real-world simulation on a 2D map. Before doing so, we have to differentiate between emitter-only definition and localized emitters, because there are some basic differences. If you're only defining an emitter without the map, you only have access to an isotropic receive antenna, and the receive antenna has no antenna scan. But if you're using the 2D map dialog, you can also have access to antenna patterns and antenna diagrams for the receiving station. The emitter can be defined with a sequence, an antenna pattern, antenna scan type. Same is true for the 2D simulation. For the emitter-only simulation, we do not account for free space loss. You directly define the receiving power at the device under test. Whereas on the 2D map, we can consider a free space propagation model. On the 2D map, you define the ERP of your transmitting stations. On the 2D map, you can also have interferers, like a telecom interferer, for example. You have a full graphical visualization if you're working on the map, giving you the 3D representation of what has been defined. And in the map dialog, you have access to multiple emitters simultaneously. Here is an example how it looks like. In this example, you see 3 emitters and 1 interferer. The emitters are sitting here, the receiver is sitting in the middle, and the interferer is sitting here. I used a GSM base station as an interferer. In order to create all these signals, you have to assign these signals to a baseband in a signal generator. If you click this button, you see a list of all the signals that have been defined. Now, all these signals must be transferred to a certain baseband in a signal generator. Here you see an example of 4 basebands in the SMW 200A. So all these signals now need to be transmitted to a certain baseband in order to be played by the signal generator. So now let's look at some examples. We start with a very simple example. We look at some pulses and sequences first. So the test case is very easy. The test case says the customer shall generate a pulse with an overshoot, a ripple, a droop, and a defined rise and fall time. Here is how this can be defined. We have seen this dialog before. This dialog allows to define an overshoot on a pulse together with a rise and fall time. It allows to define a ripple with a rise and fall time. It allows to define a droop with a rise and fall time. And it also allows to define all 4 effects together. Now, after having defined these characteristics, the pulse is generated and transmitted to the signal generator. Now, in order to analyze the pulse, I use the NRP Z81 power sensor. The data is collected by a PC and is displayed in the PowerViewer Plus software. And if you remember the defined pulses before, we exactly see what has been defined. In the first image, we see the overshoot. In the second one, we see the ripple. In the third one, we see the pulse droop. And the fourth pulse has all four effects together. In the next example, the test case is more complex. I want to define 25 pulses with linear FM, 5 MHz chirp deviation, and an interpulse modulation according to a certain table with different PRIs and frequency hops. All the pulses shall be followed by a blank time, and the total signal length shall be 3 milliseconds. So now let's have a look at what shall be defined. So first we need 10 pulses which have a certain PRI. They are followed by 5 other pulses which have a different PRI. And then there are 10 pulses which have a third PRI. And then there's the blank time. I'm using these values here for the signal definition later. In addition, I want to have frequency hops. So I'm increasing the offset frequency from pulse to pulse by 1 MHz first for the first 10 pulses. Then I leave the carrier frequency as it is. And then I want to have frequency hops of plus minus 20 MHz from pulse to pulse. Here are the numbers which I will use later on for the example. If you're using frequency hops, it's also interesting to look at the phase. In the staircase case, you see that there is a change of phase slope from pulse to pulse. This shall be shown by the green curve below. So before looking at the measurement results, let's see how this sequence is defined. So first, we look at the sequence definition. We can do so by opening this dialog here. Here you see the items that are being used. I'm using a pulse and I'm using a filler. For this example, I'm using pulse 1A, which I have defined before. If you click on the settings dialog, you have directly access to the pulse. You have access to the timing tab, to the level tab, to the modulation on pulse tab, and of course to the marker tab and some general information. If we look at the modulation on pulse, you can directly see that I'm using a chirp. You can also look at the envelope if you access this tab. If you go back to modulation, you can go back to the modulation on pulse. In addition, we said that interpulse modulations shall be used. If you click on this tab here, the dialog opens. You directly see that there are two different interpulse modulations used. The first one works on the timing parameter. The second one works on the offset frequency parameter. So let's see how the timing parameter is defined. You can do so by opening the dialog of the stagger, so to say the timing PRI parameter, and you see that there's a list behind. If you click on this button here, the list opens. There are 3 different values. These are the 3 different PRIs that are being used. In addition, you see here the repetitions. The first one means that the first pulse is repeated 10 times. Then the pulse is repeated 5 times with a different PRI. And then the pulse again is repeated 10 times with 550 microseconds PRI. If we look at the frequency hops, we can do the same thing. We can edit the list. You see there's a list behind. And we can also look at the list. In the list, we did a staircase. So I'm adding 1 MHz from pulse to pulse as frequency offset. Then there are 5 pulses where there's no frequency offset. And at the end, there are 10 pulses where I'm alternating the frequency offset with plus minus 20 MHz, which you can see here. The frequency hop work on the frequency offset. The stagger works on the PRI parameter. Of course, you can also define additional interpulse modulations. If you open this tab here again, you have access to a new interpulse modulation, for example, and then you can decide to what parameter you want to associate the interpulse modulation with. So it could also be phase or level, for example. But this we don't use for this example here. So now, if you look in this dialog, you directly see that for delta frequency, you see an indication that we are using a variable frequency offset. If you look at the PRI parameter, we also see that we are using a variable PRI. So that's why there are no values assigned. For all those parameters which we have not defined in the pulse modulation for, you can see static values, which we leave with the default values. At the bottom, you see the block diagram of the sequence. So there are 25 pulses and there is the filler. So now the sequence has been defined. So let's look at the waveform generation block. You can do so by opening it, and here you have different tabs. In the clock and duration tab, you select what clock rate shall be used. You can leave it to automatic, or you can set it to a manual value. The duration can also be defined. You can set it to one single sequence, so to say the 25 pulses plus the filler, or you can also set it to a fixed duration, as you want. Once a signal has been created, it is stored in a memory. You have access to the memory by opening it. If you zoom out and you press the play button, you directly can see the sequence. So first we see the pulses where we have the staircase frequency offset, then we see the pulses where there's no frequency offset, and then we see the pulses where we have plus minus 20 MHz frequency offset from pulse to pulse. And then at the end there is nothing because we added the filler. So here, this is a nice tool to preview the sequence before actually looking at it at the analyzer. You can also store the sequence in a repository. You see this arrow, which will deliver the IQ samples to a repository to store them inside the software. So once this sequence is created, you have to decide what signal generator you want to use. For this example, I'm using SMW. So here you have the choice either to send the IQ samples to a file or to a signal generator. If you send it to a signal generator, you can choose what signal generator you want to use. So here I've defined a couple of SMWs. For this example, I'm using SMW2. So now let's look at the signal that has been generated by the software. Again, I'm using the Z81 power sensor together with a PC, which is evaluating the data. If you remember, we wanted to create various pulses which have a different PRI. This is the middle picture. At the bottom, you see the measured sequence. There are the pulses which have the different PRIs, and the pulses are followed by a filler. In addition, there were frequency hops which should be applied. So here is again what has to be done. So there shall be the staircases, then there shall be no frequency hop, and then there shall be the frequency hops of plus minus 20 MHz. The software allows you to have a preview. This is what you can see here. So here you see the pulses, how they are created. You see the frequency hops in the waterfall diagram. Now we are coming to the last 10 pulses, and you clearly see that the frequency is hopping by plus minus 20 MHz. This is only the preview in the software, so it's very convenient to see if your signals are defined correctly. After having defined the signals, you transfer to a signal generator and you measure it with a signal analyzer. And the result can be seen at the bottom. So again, you see 10 pulses which have the staircase. Then you see 5 pulses which have no change in the carrier frequency. And then you see the pulses which have a frequency hop of plus minus 20 MHz. So now let's look at some emitters and localized emitters and how they should be defined. Here's the test case. So the test case says there shall be an emitter which has 3 antenna turns with an antenna diagram. If you draw a graphical representation, the test case looks like this. So in blue, you see the pulses which have an amplitude modulation according to the antenna diagram. For this case here, I just used 3 antenna turns. So now let's look how it looks like in the software after having defined the antenna diagram and the emitter. In a preview, you have access to what has been defined. You can clearly see the antenna diagram and you see the emitter antenna scan, which has been a circular scan. You see the receiver, which is an isotropic receiver, which has no scan at a fixed location, and the emitter has no back lobe. On the left-hand side, you have access to a simulation tool, which allows you to choose a certain period of simulation. You can also start and stop the simulation in a preview window. If you do so, you see exactly what has been defined. So you see the antenna diagram, which has been defined, which is the sinus X over X antenna. As there have not been any back lobes, you see that there's first nothing, then there's the antenna diagram with the main lobe, and again there are the back lobe region where there is no signal. This is only the preview. After having defined the signal, you transmit it to the signal generator, and the signal generator is playing the signal. In order to measure it, I used a Z81 power sensor together with a PowerViewer Plus software on a PC. At the bottom, you see what has been measured. Over time, you see the pulses which are influenced by the antenna diagram. In the middle, there is the main lobe, and you have also the side lobes with the characteristic side lobe suppression according to the antenna diagram. So now let's look how the emitter can be configured. I've prepared an example here. Let's open this one. Now you see that the block diagram has changed. We have now an emitter block here. We can look at this emitter by opening the dialog. Now you have all the items available which compose an emitter. So here we have now antenna diagrams and antenna scans that can be used for the emitter. They can be combined to a mode. Here I'm using the mode which I called pencil. You can also add additional modes. For example, a surveillance mode. In the surveillance mode, you can also use different antenna diagrams and antenna scans. There's a list of predefined antenna diagrams and antenna scans available. But you can also import your own measurement data for your antenna diagram. So let's go back to the pencil. In addition, as we've seen before, I can select also a sequence. Again, I'm using the high PRF sequence which I've defined before. If you want to use a different one, you can do so. There are many more. So now we have the same blocks as we had before for the sequence. We again have the waveform block, we have the memory, and we have the definition block of the signal generator. If you press this 3D button, you have access to a preview. You can see the defined antenna diagram and you can see the defined antenna scan. In this case, you're seeing the sinus X/X antenna rotating. At the bottom, you see the preview of the normalized power level, which you might expect at your receiver. So now let's generate the waveform and directly look at the analyzer how the generated waveform looks like. So now the waveform has been transferred, so we now look at the analyzer. So now let's look how to measure the defined waveform. For this I'm using a FSW. I'm operating the FSW in zero span mode, so I can see a time domain representation of the defined waveform. You can nicely see the sinus X/X antenna diagram, starting with the side lobes first, the main lobe in the middle, and the side lobes for the other part of the antenna diagram. In the next example, we will consider one localized emitter together with a receiver on a map. The localized emitter is sitting somewhere and the receiver is sitting in the middle. The map has a certain coordinate system which allows to define the location of the emitter. At the top, you have a display options at the map. Those allow you to select what information you want to see on the map. You have choice to select, for example, the level, the ERP, or the carrier frequency if you need. If you don't need this information, you don't need to display. In order to put the emitter on the map, you can simply drag and drop the emitter out of your emitters defined onto the map. You see an instantaneous display of the receive level and the distance between the emitter and the receiver, as I said before. You also see the attitude information, the bore side information of the emitters. You can also display the emitter and interferer names, for example. Once all the definition has been done, you again have access to a preview tool. In the preview tool, you see the line of sight between the transmitter and the receiver. You see the emitter antenna diagram, you see the emitter circular antenna scan, for example, and you also see the emitter location on the map. In the middle, you see the receiver. The receiver is carrying an antenna. The receiver antenna is following a certain scan type, for example, a raster scan. And also, the receiver has a certain attitude information. Before generating the signal, you can access the preview, which allows you also to select a certain preview time. In the visualization dialog, you can select if you want to see the full antenna patterns, if you only want to see the scan or the half-power beamwidth representation, for example. If you have longer or slower scenarios, you have access to a slow motion factor, for example. As before, you can start the preview, and in the preview you see, according to the selected preview time, what is happening in the simulation. In this case, you see 4 antenna turns, the first one having a lower level, the middle one having a higher level, and the last one again having a lower level. This is coming from the raster scan of the receiver, which is scanning the emitter antenna under different angles of its antenna diagram, and therefore leading to different power levels. So now let's really have a look in the simulation software. On the left hand side, you see a couple of examples. I'm choosing example 5, one localized emitter. On the map, you can now see there is one emitter and there is one receiver. They have a certain distance to each other. If I access the emitter, I have access to all the properties. So first, let's look at the antenna pattern of the emitter. For this emitter, we have chosen a sinus X/X antenna. The antenna pattern can be previewed in 3D in this view. We have also selected a certain antenna scan type. Also this one can be previewed. For this emitter, we have selected a circular scan. Also this 3D preview allows to see what has been configured before really creating the signal. The same can be done for the receiver. Also the receiver is equipped with an antenna pattern. Also this pattern can be previewed in 3D. For the receiver, we have chosen a Gaussian beam. This beam can be previewed here and has been defined before. In addition, also the receiver antenna is following a certain scan. In this case, we have selected a raster scan, which you can see here. So this is the scan type which has been selected for the receiving antenna. Now we have seen each item separately, so we can also have a preview of both items together, so emitter and receiver. We again select this menu and select 3D view with receiver. What you can see now here is the 3D representation of the configured scenario. In the middle, you see the receiving antenna following a raster scan. On the left hand side, you see the emitter antenna, the sinus X/X antenna, following a circular scan. At the bottom, you can get a preview of the calculated signal. In this case, you see 4 antenna turns of the emitter antenna. Now, you see the effect of both antennas and scans together. You can only switch to emitter only. Then you only see what effect the emitter antenna would create. In addition, you can also do the same for the receiving antenna. If you only want to see the effects the receiving antenna is creating, you just select receiver only. And then you only see the signal as it would occur if the receiving antenna would be alone. So now the signal shall be created. Here is again the scenario which we had. It's the receiving antenna in the middle with the raster scan and the emitter rotating on a circular scan with the sinus X/X antenna. After the signal has been created, it has been transferred to the signal generator. I used again a Z81 to measure it. In order to nicely trigger, I'm using a special trigger box in order to always trigger on the start of the scenario. And this is what you get. If you remember, we defined exactly 4 antenna turns. If you remember, the first antenna turn had a lower power level than the middle ones, and the last one also had a lower power level. The reason again is that the raster scan of the receiving antenna is looking at the emitter antenna under different angles and therefore leading to different power levels. But this is exactly what is happening in reality. The distance between 2 of these peaks is exactly 1 antenna turn. The drop of power level corresponds to the antenna scan type of the receiving antenna and the antenna pattern. If you zoom in, you see again what has been defined. As I said, we are using the sinus X/X antenna for simplicity, and if you zoom in, you directly see the nice antenna diagram of the emitter again. So now I will show you how to create a scenario from the beginning. You have to access the 2D map by clicking on the 2D button. In the middle, you see the receiver. This receiver already has some properties which I have defined before. It is carrying a Gaussian antenna beam and it is doing a circular antenna scan. Of course, you can also give a certain gain value to the receiver. In addition, you have access to pointing parameters. So now, let's drag and drop some emitter onto the map. By doing so, you access the emitter dialog, you select the emitter you want to drag, and you just drop it on the map where it is needed. You can place it with the right spacing from the receiver. Now let's make it a little more complex. I'm adding an interferer, so I select the waveform dialog, and for this example I will select an LTE interferer. Let's double click it and preview it, and you will see that this interfering signal typically looks like an LTE one. So now let's close this, drag the LTE signal onto the map and place it where it is needed. So now we have to define the frequency of the LTE signal. We can do so by going into the properties and giving it the right carrier frequency. In addition, we also have to use a reasonable ERP. So now the values are changed. In this table, you have an overview of what has been configured. Now we can look at the scenario, how it looks like. We can do this by using the 3D preview. Here, we see the emitter antenna and the receiving antenna, both rotating. At the bottom, you have access to the preview of the signal as it would look like. The same can be done for the LTE interferer. We can also access the 3D preview, and here we see how the signal would look like just coming from the LTE interferer. If you select the same period, it is comparable to the signal before. Now you will see the peak which is coming. Now we have defined all the emitters and the interferer. Now they have to be assigned to the signal generator. You can do so by clicking on the Assign Emitters button. And now you move the radar emitter to one path of a signal generator, for example SMW, and you move the interferer to the other path of the signal generator. You can now generate the signals in each path and combine them with an RF combiner, or if they are close enough in frequency offset, you can also use the stream mapper, add both signals digitally and output them at the RF port of the signal generator. What you can see here now is the measurement of this scenario. You're looking at a screen of a FSW. I'm operating the FSW in zero span mode. I normalized the maximum RF output power of the radar emitter to -10 dBm to have a better view. On the left hand side, you see the first sinus X/X antenna diagram of the radar emitter. Then you see the signal coming from the interferer. And on the right hand side, 75 milliseconds later, you see again the sinus X/X antenna diagram from the radar emitter. So 75 milliseconds is exactly one revolution of the radar emitter. In addition, the receiver in the middle also had an antenna diagram and an antenna turn. So in total, what you see is exactly the signal as it would occur at the output of a rotating receiver antenna having a certain antenna diagram. So now let's look at the next example. This example is a direction finding example. Let's look at the test case. There's a single emitter and there's a receiver in the middle. The receiver is having now 4 antennas as you need to generate multiple receiving signals. In order to generate this test case, you need to have 4 phase coherent RF signals. So now let's look how these 4 phase coherent RF signals are generated. The SMW provides 2 RF signals which can be phase coherent. As we need 4, we have to extend the SMW by additional SGU, SGS extension boxes. In order to make them phase coherent, all 4 RF channels share the same local oscillator signal. In order to account for the phase differences, which are coming from the different location of the receiving antennas, we can make use of the baseband offsets. In the baseband offsets, you can put in the different phases coming from the different locations from the receiving antennas. In order to account for timing, we have the chance to trigger all basebands at the same time. In order to account for delays coming from different cable lengths or different delays coming from the SGS SGUs, we can compensate these delays in the IQ modulator by adding just an IQ delay. Now everything has been defined. This is how the test system looks like. It consists of a SMW 200A extended by SGS SGU extension boxes. They all share the same local oscillator. There are 4 RF output signals. In order to verify the performance, you can use an RTO, for example. In addition, you can also use a ZVA or ZNB. In this setup, I will focus on the RTO in order to show you the performance of the phase coherent signals. So now we directly switch to the screen of the SMW. From left to right, you see the 4 basebands, which actually correspond to the 4 RX antennas. They are followed by a stream mapper, which allocate the different streams to the RF outputs. One stream is directly output at RF chain A. The other stream is directly output at RF stream B. Stream C and D are output at the digital interface and at the analog interface. All the channels share the same local oscillator, so there is no difference. Now, as the system is phase coherent, I have access to the baseband offsets. I can now adjust the phase of baseband B and move the signal with respect to all the others. So now you see the green curve moving. I can do the same with baseband stream C. Also here I can move the phase and therefore shift the signal with respect to all the others. And the same can be done with this baseband stream D. I can also move the signal with respect to all the others. By these baseband offsets, I can now adjust any phase front which is required. In the last example, let's look at some multi-emitter environments. Here's the test case. The test case consists of 3 emitters, which have all the characteristics which we have explained before. Again, we have the receiver sitting in the middle. And in addition, we have an interferer, which could be a GSM base station, for example. In order to generate the signal, we can use the following setup. At the top, you see again SMW 200A, which is equipped with additional extension boxes SGS and SGU. The pulse sequencer software is providing the 4 ARP files corresponding to the 4 contributors, like the 3 emitters, which I have said before, and the interfering signal. As we need 4 RF signals at 4 different RF output frequencies, again the SGS SGU extension boxes are needed. If you apply all these signals to the signal generator, switch on the IQ modulator and the RF signals, you will see the spectrum which is depicted on the right hand side. So you see the 4 signals, the GSM interferer and the 3 radar signals. If they shall be measured, you can combine them with a power combiner and directly inject them into a spectrum analyzer. In the last test case, there are no radar signals now. Here we are focusing on communication signals. So there are communication stations around in the map. For this example, I selected 8 stations. All these stations, of course, also have a waveform type, they have a certain ERP, and they have a carrier frequency. In the middle, again, there is the receiver. All the communication stations have a localization, so to say they have X, Y, Z coordinates. They have a certain attitude, and of course we have to use the propagation model in order to account for the free space loss between the interferers, the communication stations, and the receiver. In this setup, you see how this example can be simulated. The pulse sequencer software is generating all the waveform files. They are transmitted to the SMW 200A. As we are now needing 8 RF outputs, you have to extend the SMW by additional SGT boxes. They can receive their signals from the digital interfaces which are provided by the SMW. If you cable the system and if you combine all the output signals via an RF combiner and measure it with a spectrum analyzer, you would see the spectrum as shown on the right hand side. So you see all the 8 signals coming out of the SMW and the SGTs according to their carrier frequency. In this test case, they can all have an instantaneous bandwidth of 80 MHz. If you want to simplify your setup, you can also use the SGT signal generator standalone. In this case, you also generate all the waveform files, you transmit them to the individual signal generators, and output them there. You use an RF combiner in order to combine all these signals, and you can also measure all these signals together with a spectrum analyzer. On the right hand side again, you see the spectrum which you would get. So in this case, you get 8 signals which can have 160 MHz bandwidth each. If you need additional information, you can access our webpage under rodeandschwarz.com and access SMW and look at the options K300 or K301. If you need more information, you can also read our application cards. There's an application cards on the pulse sequencer software, and there's also an application card on multi-channel phase coherence setups.